Okay, let's talk about these gas generator parameters. So what do I mean? Well, if I'm actually going to have a jet engine, there's certain things that I really care about, certain parameters that are going to help me determine what my jet engine should look like. So first off is my pressure ratio. That's simply saying what's the difference in pressure between here and here. That's going to be a function of what my burner function at, like what pressure does it work effectively at, and also just how fast I'm going. Then my air mass flow. You know, if I got a bigger plane, I'm going to have more mass flow. We'll hit on each of these as we go further forward. The turbine entry temperature. I can't just heat things up forever after all. Eventually I'm going to melt my turbine blades. That would not be good. And our fuel heating value. The better the heating value, the less fuel I need. And finally, how efficient are each of my components? Maybe I have to do 2 stages of compression and expansion, maybe just 1. It'll all depend on what I'm looking at for my individual system and also the Mach number I'm at. So let's look at these, really focus on a few of these, not all of them, just a few. And we'll see most of these as we go forward. Okay, so first off, let's look at the total pressure ratio. Now, this is going to be a function of 2 things. One, our combustor has a particular pressure that's going to work effectively at, right here. Also, our flight Mach number will help us determine, 1, the type and number of stages I'll need for compression. Like, for example, you might be thinking, like, why does Mach number matter? Just compressing it, you know, it's atmospheric outside and not atmospheric inside. Well, think about it this way. If I'm going supersonic, I've got a shock wave. That shock wave is acting as a compressor. And so, you know, I don't need a compressor anymore if I've got a big enough, strong enough shock wave. Or even if I don't have a shock wave, if I'm going pretty fast, I begin to compress my flow just by running into it. No shock wave yet, but it is increasing the pressure. And so the amount of stages I would need to get the same compression will be reduced the faster I go, till eventually I don't even need a compressor. So this guy right here, that's a ramjet. Oh, went too far. Ramjet doesn't have a compressor. As you can see, it doesn't have a turbine either. Why? Because it doesn't need a turbine because it doesn't have a compressor to run. And so ramjets are amazing. If you're going supersonic, they are more or less just like a rocket that carries its own, doesn't have to carry its own oxidizer. And they can get you going really, really fast. And they don't need that compressor because they've got a shock wave doing that for them. Okay, so here's our first one, our total pressure ratio. It's simply saying how much do I have to increase pressure so that I can have it on my combustor act efficiently. Let's keep going. So the second one is our air mass flow rate. If you think about it, a really small commercial jet and a huge commercial jet, well, guess what? They weigh incredibly different. This one is heavy. This one is light, comparatively. I don't think I could bench it. And so if I have a light aircraft versus a heavy aircraft, I'm going to have to be pushing a lot less or more air through it to produce the thrust I need to stay in the air. That's why this guy has 4 jet engines and this guy has 1. This one has a giant jet engine, this one has a small one. And so the small one has much less mass flow rate and it's able to still keep that plane in the air. So in general, other things this does is the larger my mass flow rate, the larger my jet engine. So it has a larger face diameter. And as such, there are going to be a lot of other like structural concerns you have to deal with. Okay, let's keep going. So the last one we're going to focus on is our turbine entry temperature. And as a note, the other 2 we will see, component efficiency and our heating value. We'll see this as well, but we'll stop with this one. So the turbine entry temperature is just the parameter, which is simply saying that if you heat it up enough, this will melt. And if it melts, you don't have a jet engine anymore and you die. So let's not make it melt. So what do? Well, for one, you're going to be taking some of your air that's colder from up here, and you're going to stick it in here and say, okay, let me cool you down so that you are not too hot and melting everything. Or I might have, some other technology that's going through my turbine blades that's constantly cooling them, even though the temperatures outside of those are enough to melt them. So there's different things I could be doing. The last one, typically you're not going to get anywhere near the melting temperature, but you're going to have significant technology to cool them. So the hotter the flow coming out of your combustor and the lower the temperature these turbines can take, the better your cooling technology has to be. So you can either find better alloys, better cooling technology, some combination thereof, to mess around with this. So this is another parameter that we're going to have to care about as we go forward. Now, for us in this course, we don't care about like what the exact technology we're using for cooling is, but you still need to know that's something we're thinking about. We have to think about that as we go forward. Okay, so that is it for this section. Thank you so much for listening. I hope this helps you, and we will really get into analyzing our gas generator next time. Have a good one. Bye-bye.